Okay, so in this question and answer session, what I'm actually going to do is two things. First of all, no, can you leave the lights on, please? Because otherwise it's impossible to see from the back if I use the board. So, the first thing is to, okay, what I'd like to show, I mentioned this bird trap basis. And I'd like to show you how that works because if nothing else, for the experimentalist, it's going to be a matter of group theory. But if you're a theorist, this is absolutely a wonderful trick that's known to some extent by a lot of people. Professor Reinhardt told me in the late 70s he used this to compute Clebsch-Gordon coefficients. I know it from a book by Predrag Cvitanovich that's online that I'll mention. But let me first of all start out with the usual generators for SU2. So for SU2, you know you have 0, 1, 1, 0. Sigma 2 is, I may get, I think I wrote it down so I took the sign already. It's important to make sure we get, I didn't. Whatever. I minus I, 0, and sigma 3 is 1 minus 1, 0. Okay, fine. So these are the usual Pauli matrices that you're familiar with, and they satisfy, of course, commutator sigma 1, sigma 2 is what? This is going to be I, 2I, sigma 3, and so on. Now, I mentioned ladder generators. Ladder generators are very convenient. You can show that, for example, sigma plus, and here I probably will get the notation. The sign 1, sigma 1 plus I sigma 2 is, well, I'm going to normalize it differently, but it won't matter. It's basically 0, 1, 0, 0. And sigma minus is going to be the opposite, 0, 1, 0, 0. And these are very nice because if you take this and you commute it with this, let's work that out. Sigma 3 with sigma plus. So what am I going to get? I'm going to get 1 minus 1, and 0, 1, 0, 0. So this is going to give me what? That's 0, that's 0, that's 1. So I get a 1 here, 0, 0. And we're not worried about the overall normalization. Minus 0, 1, 0, 0. 1 minus 1. And then again, what I'm going to get is I'm going to get minus 0, minus 1, 0, 0. So this is going to be proportional to sigma plus. So the advantage is if you take any diagonal generator, you get any commutator of the diagonal generator with a ladder generator, you get the ladder generator back. And in fact, you can show that sigma 3 and sigma plus minus is this thing times plus or minus. And there's an overall constant that I won't worry about. But what I'd like to show you, well, this has various advantages. As I mentioned, I've defined one of these sigma plus to be T12, and the reason for that is this is the first row and the second column. T21 is the second row and the first column, and you'll see later how that comes about. But if I take trace of any of these ladder generators with itself, well, if I take this matrix and I square it, it's not going to have any diagonal components. What I need to do is multiply the plus generator times the minus, and then I get something non-trivial. Now, SU2 has 3 generators, so instead of dealing with sigma 1, sigma 2, and sigma 3, I can deal with this sigma plus, sigma minus, and sigma 3. And that's the usual Karpacz basis that you're familiar with. What I'd like to do is do something that was totally perverse for SU2. For SU2, it's just like totally bizarre. What I'm going to do is I'm going to add one extra generator, so instead of having 3, I'm going to have 4. And I'm just going to take minus sigma 3. And you look at that and think, why should I ever do that? It just looks totally bizarre. In particular, the diagonal generators have a weird normalization, since this is just minus that. If I can normalize this, so it's the two different diagonal generators are equal, but then there's a cross term, because this is just minus that, so I have to get something. So it's an overcomplete basis by 1, and it appears totally perverse. What I'd like to do is show you that this gives you a way of generalizing the generators for SUM very easily, and in fact it works for all groups. So for SU3, as I discussed, and also by Professor Reinhardt, the usual basis is one where the diagonal generators are this. It's lambda 3 and lambda 8, which is up to an overall constant, 1, 1, minus 2. And then this is the SU2 cut generator. And this generalizes onto higher end. You typically take this is an SU2 and SU3, and you go on and on and on. But you keep the lower diagonal generators. Instead, what I'm going to do is I'm going to take, well, I can take this 1, 1, minus 2, and then what I can do is just shuffle that minus 2 in all the 3 possible places. So instead of having 2 diagonal generators, I'm going to have 3. And it's clear to see that, well, it's overcomplete, because if I take this plus this plus this, I'm going to get the same thing. So that's, I can certainly do that. It looks perverse, and I'd like to show you why it's not perverse, and it enables you to derive arbitrary identities in a very simple fashion. Because what I'm going to do, this C and D are, in fact, A, B, C, and D are all fundamental indices. So they all run from 1 to n. And in particular, then, delta AA, which is the sum on A from 1 to n, is equal to n. Okay? And then what I'd like to show you is that this is a representation for the generators of SU. And it's something that you can remember without knowing anything about SUN. And it's, the thing that's funny is normally, well, these are indices in the fundamental representation. You're used to those running from 1 to n. But this is an adjoint index. And so normally you're used to taking big A, where it runs from 1 to n squared minus 1. Instead, what I'm doing is I'm taking 2 fundamental indices. So this runs from 1 to n, this runs from B runs from 1 to n. So it's an n squared indices. So I have 1 extra generator. And I'd like to show you that this is the correct representation for the generator. Now, to do that, I want to show you that this is in fact a projector. And in fact, I'm going to turn it on its side, and I'm going to show you how this is a projector. So what I mean here is this is a somewhat abstract notation. But this is ABCD, ABCD, and this is equal to delta AC, delta BD, minus 1 over n, delta AB, delta CD. So it really is just a bunch of delta functions, just trivial delta functions, nothing complicated here. Let me now show you that this is a projector. So a projector means what? I do P squared is equal to P. So I'm going to take this and multiply it by the same thing. And I do this on the next slide, but looking at things, I think it's easier if I do things all in the same direction. So for example, let's multiply this times this. Well, this is this times this. And I'm not going to write the indices because the advantage of drawing bird tracks is that it's completely trivial. This is just a bunch of delta functions, you tie them together. So this is this times this. Then I have this term. Well, this is going to be minus 1 over n times this from here. And then I have that. Then I do this times that, so that's minus 1 over n. And then I have this. I tie them together, I do that. And then I have finally these two together. So that's minus 1 over n, quantity squared. I have this, this, and this. And then remember, I said the sum on the delta function is n. So this thing here, this is going to give me a sum on delta. This is going to be delta AA, sums on A, from 1 to n. And so I get n. This is minus 1 over n squared, so this whole thing is going to be plus 1 over n squared times n times this. And what I can see is that this thing is equal to this. And then I get minus 1 over n, minus 1 over n, plus 1 over n. So I'm going to get plus 1 over n, minus 1, plus 1, times the same thing back, which is just this projector in the first place. So this is in fact a projector. And that's what's nice about this basis. So you can in fact see that, and now I'm going to write this on the side. I thought when I wrote this on the side this way it looks a little more obscure, that it's over complete by 1 if I take this representation and I tie the loops on top together. So now I'm summing over these indices. So I'm just going to sum over the diagonal indices. Well, this is going to give me a straight line because I go here, up, and tie it together, I go down, so I just get a straight line. Minus 1 over n, I get a straight line, and then I have this sum that's equal to n. So 1 minus n over n is 1 minus 1, which is 0. Which is just, for SU3, the fact that these three generators are equal to 0. And you can see for arbitrary n, it's easy to see what you get. Let's consider the case of SU4. For SU4, the diagonal generators that you take in the Cartan basis would be 1 minus 1, 0, 0. 1, 1, minus 2, 0. And 1, 1, 1, minus 3. These are clearly three traceless diagonal matrices. And instead of dealing with these two, I'm getting rid of these two. And in addition to this, I'm using minus 3, 1, 1, 1. 1 minus 3, 1, 1. 1, 1, minus 3, 1. And this. Now, you might think this looks a little perverse. It's an overcomplete basis. But in fact, it enables you to do a lot of simple calculations. Primarily because the product of any two generators is itself a projector. So this is the calculation that I just did here of showing that this operator is in fact a projector. If I square it, I get back the same thing, except now I'm tying it together with these indices go up instead of to the side. I thought to the side it was a little clearer, and that when I wrote it like this, that it was clearer. Now this is a very detailed description is given by Predrag Cvetanovich in an online course book, and in a paper with Yoshimasa Hadaka, we give a very brief explanation of this. Okay, so let me show you that you can in fact use this to derive identities. So here's one identity, see, because otherwise what you have to do is, for SUN, you have to write down all of these generators. You have symmetric structure constants, anti-symmetric structure constants. And what you typically want is just some identity. You want to know if I take, say, a product of two generators, what that's equal to. So I'm going to show you, I've illustrated it here. I'm going to go through and show you what that's like. So this is TAB, and then I'm contracting it with the same times CD. So what this is equal to, just to be perfectly clear, is TAB upstairs. I have C, because this is C on the left, B on the right, so this is going to be E, TBA, ED. And notice that the lines have arrows, because this is SUN. This thing has an arrow coming in, this has an arrow going out. So when you contract indices, you have to draw lines in the proper way. So let me just show what the first term is like. So the first term is going to be like this. And then I have arrows.
Do you sum over A and B?
Yes, I sum over A and B. Yeah, summed over A and B. And so, see, the nice thing is, you don't really have to, if you use a bird tracks, all you have to do is keep track that the arrows go in the same direction. So here, this goes up, that goes down. Here, this goes up, that goes down. And I have to tie these indices together. So what this is going to do, and there's actually a factor of 1/2 in my definition of the generator. So this should be times 1/2. That this diagram is equal to 1/2 times a straight line plus a loop here. And this is equal to a delta function times n over 2. And that's that first term here. And then what you can show is the other terms. Well, here, let me show you what the last term is like. The last term is, again, there's a 1/2 because, to be clear, I've defined my generators such as a 1 over square root of 2 in the times the projector. And so let me take this term, the last term, times this term, the last term. So that's minus 1 over n squared. And then I have this times this. I have this times this. You have to draw the arrows properly. And then you just tie them together. And you get a funny looking thing like that. But again, every time you get a loop, you just get a factor of n. So this is going to be 1/2 times plus n from this loop up here over n squared. And that's this factor here, 1 over n times n over n. I dropped the 1/2. And the other two cross terms gives you each a factor of minus 1 over n, and in all, you get minus 1 over 2n. So this is the kind of thing that those of you who have to do group theory, you carry around the cheat sheet of formulas. And in fact, you don't have to carry around the cheat sheet, you just have to remember this one projector, and that's it. Now, why then, you might ask, is SUN complicated? That is, those of you who've done a little group theory know that if for SU2, I can always take the exponential of an element of the Lie algebra And I can always write this as cosine of omega plus I omega at sigma sine of omega, where omega is the square root of omega squared, and omega hat is omega over its magnitude. Fine. That's easy to work out because of the properties of SU2. Why doesn't this work for SU3 or higher? And the answer is basically because of the traces. Let me show you. If I take two matrices now for SUN, so each of these is a projector, and I've dropped the factors of square root of 2. But each is this product of delta functions minus 1 over n. I multiply them together. Well, what am I going to get? Well, the first term, if I multiply this times this, I get these two factors. If I multiply the last trace times the last trace, I get plus 1 over n squared times the delta function and these two things. And then the cross terms give me these terms. But the point is that if I take two arbitrary elements of the Lie algebra, I don't get anything simple back because of these traces. That's what messes everything up. It's all of these traces. For example, at large n, I can neglect the traces. I drop all of these terms, and I just get this, and it's nice and simple. But at small n, that's not true. To show you that in another way, let me show you the usual things that you end up needing when you compute are the symmetric and antisymmetric structure constants. This involves three matrices. Now, if I take three matrices and I make it antisymmetric, then all the traces drop out. So the three gluon vertex in this form just has the following simple form. I just tie them together. You have to be careful that you can tie the indices together in different ways. So there's a nice planar form, and then you notice that, aha, this arrow coming in can tie to that arrow going out. And you have to take into account that. On the other hand, if you work out what the symmetric structure constant is like, that's kind of ugly. And let me, I drew it kind of schematically there, so I just want to go through and draw it for you. So this is the thing, and now I have to get the arrow straight. So that's one, and then I have to take the symmetric combination. So then what I want to do is this can go in, can go out this way, so this is like that. And then this can go to there, and this can go to there. And I think I do that properly. All the arrows are going in the right way. Right. Okay. And then we have to take the trace terms. Well, the trace terms are, you can show that minus 2 over n. Well, I can tie one trace together, like this. And let me get the arrows straight. And then I can add this. So again, and then finally I have one last term plus 4 over n squared. So this is what you would write down as D, A, B, C, D, E, F. The symmetric structure constant that doesn't exist for SU2. And in fact, you can check that if you take a trace, remember this is an overcomplete basis, so if I tie this together, if I sum over anything, that the whole thing should vanish. And you can easily see that that's true because if I do this, all of these things are going to collapse to just something like this. And what I'm going to get here is all of this is going to be equal to, this is 2. I'm always going to get factors of 1 over n. And you can show that the whole thing cancels. I'm not going to do this here because I'll probably mess it up. Let's see, can I? No, I think I can do it. This is 2 minus 2 over n times this. And then if I do this, I'm going to get, yes, minus 2 over n from these two with no extra n times this thing. Minus 2 over n times 2. This is plus 4 over n squared. And then if I tie this together, I'm going to get an n, and I'm going to get this. So this is minus 4 over n plus 4 over n. That cancels. This cancels. So I can do simple algebra. Okay. But it really is a very useful thing. If you don't need to do group theory for SUN, then you don't have to worry about it. But if you ever do, it's a very nice thing. And for example, you can show, well, I derived this relation all the way. And the reason why we did this is because we wanted to take a background field that was arbitrary. See, the thing that's funny about the standard basis, while I erased it, is that it chooses a preferred direction. And we want a basis where there's not a preferred direction. So, okay. So that was the first thing I wanted to go over. And then I'll go over the problems. Are there any questions before I go on?
Is this to be a copy identity with this?
I'm sure, I forget what the Jacobi identity
So that
is.
you have
The product of 3, the commutator of the
that
commutator?
yes, and there's a side B. Permutations of these. And this is supposed to be 0.
But it's commutator T of commutator T summed over all of them. I'm sure you can, but I'm not going to embarrass myself by trying to do it, since I haven't done it for
You
years.
can give it as an exercise to students.
That would be an excellent, but there must be a clever way of, I'm just wondering if you could see.
Easy.
Yeah, because you don't want to do things hard, right? You want to do things in a simple way.
And you advantage this as a useful tool to do simple stuff.
Yeah, I'm just wondering, because see, what's nice is that the commutator, this is directly a representation of the commutator. Yeah. It must be because basically that all of these trace terms that enter into the symmetric structure constant drop out for when you take the anti-commutator. That's really what makes the anti-commutator simple. Are there other questions? Okay, if not, then I'm going to go on to the problems that I gave you. And I'm just going to go ahead and solve them because it's the end of the day. Some of you have been very heroic in sitting through everything. If I can't say it's really a lot to absorb, and it's difficult. One's brain, I usually find I can only remember 1 or 2 things, so if you've remembered at least 1 or 2, I think you're doing very good. Okay, so the first 2 problems have to do with just the kind of invariance that one can write down in terms of a sigma model where you have, first of all, the usual chiral field where phi transforms. Alpha is the phase for axial U1. And U right and U left are for SU left. SU2 left plus SU2 right. And you have a tetrachord field with charge -2, that's a scalar. And so the first thing I ask is to Write down the terms that are invariant under axial U1. Well, if it's axial U1, every time you have an e to the I alpha, you have to make sure that the alphas disappear. So the simplest terms that you can write down just involve products of phi dagger phi. Because wherever I have a phi and an e to the I alpha, if I have phi dagger, I get e to the minus I alpha. And this is, I should say, a 2 by 2 complex matrix. This is not the kind of representation I used where it was an O4 or an O8 vector, because it's easier to write down the invariants here. And then you could consider, well, if this is invariant, I can take trace of phi dagger phi, complex conjugate squared, that's clearly an invariant, and trace of phi dagger phi, complex conjugate squared. Now, you might ask, why can't I take, I introduced determinant phi, so why can't I take determinant of phi dagger phi? If phi is a 2 by 2 matrix, this would also be a quartic invariant. And in fact, you can show that this is equal to a sum of these. And let me convince you why that's true. Phi dagger phi itself, phi is an arbitrary complex matrix, so I don't know anything about phi. But phi dagger phi is Hermitian. And what that means is I can diagonalize it. So I can take phi dagger phi equal to a matrix AB 0, 0. Because if I take phi dagger phi, A and B have to be real. So this is phi dagger phi is equal to A and B. And then if you do that, you can easily show that this is equal to 1/2 times trace of phi dagger phi squared minus trace of phi dagger phi squared. And this really is easy because if phi dagger phi is equal to AB, this thing is A plus B squared. This thing is minus A times B. And this whole thing is then, wait, did I do? No, A squared plus B squared. And this whole thing is A times B, which is exactly equal to the determinant of this matrix. So, okay. So we don't have to worry about this term. And then you can write down other terms involving zeta. But if we require invariance under axial U1, well, we can obviously take complex conjugate of zeta squared, the square of the complex conjugate squared. And then there's a term that was first written down by Francesco Giacosa and collaborators, and that's zeta times the determinant of phi plus complex conjugate. And this is cute because zeta has charge -2, determinant of phi, it involves 2 powers of phi, so it's going to be e to the I alpha squared, and so this whole thing is invariant. And there's clearly one last term one can write down, which is zeta squared times trace of phi dagger phi. And that's all I can do. So these are the U1 and U axial U1 invariant terms. And I believe that's all one can do. And the interesting thing, as I said, is this novel term that mixes the tetraport field and a term that looks like it's due to the anomaly. So this term will persist at arbitrarily high temperature. And that's why it's of interest. Okay, and then let's go on and write down the terms that are invariant, not under axial U1, but only under the Z2 symmetry. And I'll write down how things transform again. So phi goes to e to the I alpha u right, phi u left dagger, and zeta goes to e to the minus 2I alpha times zeta. So here the Z2 symmetry just means if I choose alpha equal to 0 or pi, that the field is, this field is invariant. Okay? And then the various terms that I have. Yeah. Well, one term that's invariant just under this is determinant of alpha, of phi, because this transforms like e to the 2I alpha, determinant of u right, phi, u left, dagger, and a product of determinants, this is equal to u right, determinant phi, determinant u left, dagger. So these are equal to 1 because they're SU2 matrices, and this is invariant if alpha is 0 or pi. And this is in fact the usual representation of the anomaly for two flavors. Now when you go beyond to quartic terms, you get a whole bunch of other terms. And let me just stress that before I showed that determinant of phi dagger phi was equal to a bunch of traces. If phi dagger phi, since phi dagger phi is Hermitian, that's no longer true if phi isn't Hermitian. If phi isn't Hermitian, determinant of phi is not equal to something like trace of phi squared plus some constant trace of phi squared. And it's very easy to see that because now phi is an arbitrary complex matrix. So you can take a special case, you can take phi to be totally off diagonal. Say something like this. In this case, determinant of phi, well, the diagonal elements give you 0, but the off diagonal give you plus AB. Whereas these traces, if the matrix has the following form, won't reduce to anything simple. So this is a new invariant. And you can show that you have various other terms. You have determinant of phi plus complex conjugate. That's the trace of phi dagger phi. You can also have determinant of phi squared plus complex conjugate. This is an independent term. These are all the terms involving the phi field itself to quartic order. And then you have other terms like trace of zeta times trace of phi negative phi plus complex conjugate, zeta squared times determinant of phi, and I believe that's it. Okay. So that was just kind of an exercise, which was the main thing we went through in our paper. It means when people talk about, even for two flavors, the linear sigma model, they typically don't include these other quartic terms, but in principle they are there. Okay, so let me go through them and show you what happens for three flavors. So it's the same sort of thing. The axial U1 charge is the same, and as I show, I get now zeta transforms under SU3 left plus SU3 right in the same way as the usual chiral field, but it has a different axial charge. It's still -2 relative to +1 because it's a diport field. And it's -2 instead of +2 because when you have to include the representations in terms of the underlying field. So for axial U1, the invariants that you get, well, you get the usual invariants. I won't write them all down. You get trace of 5 dagger 5, trace of this squared, and so on and so forth. You get one new term, which I wrote down, which involves. Now you have to recognize that this is phi AB, this is epsilon AB. One of these is a left index, the other is a right index. I've ordered them so they're the same. So what I can do is I can use epsilon symbols and tie things together in the following way. So I've tied 3 SU3 right indices together with an epsilon symbol and 3 SU3 left indices with an epsilon symbol. And this transforms like e to the I alpha. This transforms like e to the minus 2I alpha. So as I said, it's invariant under axiom U1. So it persists at arbitrarily high temperatures. The other terms you can write down that are axial invariant are just like, well, there's, for example, trace of phi dagger phi, trace of zeta dagger zeta, and so on and so forth. And you just tie things together. That this is what I wanted to go through. It's fun. All you have to do, wherever you have a phi, you put in a phi dagger or a zeta dagger. So I can write down trace of zeta dagger zeta times trace of phi dagger phi. This is clearly going to be invariant under SU3 left plus SU3 right because they transform in the same manner. And as long as I have a dagger and a field is going to be the same. It's going to be invariant under axial U1 because wherever I have a phi dagger, wherever I have a zeta dagger. So I can write down other terms, but it's just a matter of writing them in a different order. So I can write zeta dagger phi, phi dagger zeta. This is in principle a new coupling. So this is also invariant under SU3 left plus SU3 right and the axial U1. And then I can type, instead of taking a single trace, I can take 2 traces. And so I can put the phi's together, the zetas together, or I can mix them up. So I can take zeta dagger phi times trace of phi dagger zeta. And that's all I can do. So these are the couplings invariant under axiom U1. And let me now go on and show you what the couplings invariant under Z3 are. So again, phi goes like e to the I alpha, U right, phi, U left dagger. Zeta goes to e to the minus 2I alpha, U right, zeta, U left dagger. Well, the usual anomaly term that you write down is determinant of phi. So I can certainly do that. That's where it's at, so U1. To Z3. I can write down determinant of zeta. That certainly works. And then I can write down this funny term involving 2 epsilon symbols by taking 1 phi and 2 zetas. Because this transforms like e to the minus 4I alpha. This transforms like e to the I alpha, so it's e to the minus 3I alpha. So that is, I can take charge minus 2, which is minus 4, plus 1, which gives me 3. That's why it's invariant under Z3. This is in contrast to this term, which has charge minus 2, plus 1, or 0. Okay, so you get that funny cubic term, and then there's lots of terms you can write down that are invariant under SU3 and I'll stop writing the complex conjugate because all I have to do, I just make sure that things are some field dagger, field dagger, field, but then I can mix them up in any possible way. So I can take 3 sides and 1 phi. I can take 2 sides and 2 phis. I can take 1 side and 3 phis. And then I'll let you write down there are 3 other terms involving 2 traces that I'll leave for you as an exercise. So this is how we end up with a model with like 20 different couplings. But that's what's dictated by the symmetry. And that's what the general Lagrangian is like. So, are there any questions? Because then I'll go on to the last problem and probably end early and spare you some torture at the end of the day. No? Okay, so the last problem was a trick. And I hinted that. And then I thought I should make you work hard, and then I thought about it, and I hate working hard. So the problem was, take the general Lagrangian in a linear sigma model. So you have trace h of phi dagger plus phi. So this is the term that breaks the symmetry. You have a mass term. You have an anomaly term. And then I was somewhat easy, I said just take one term, although it doesn't really matter, as we'll see. And what I wanted you to show is to derive the Hoof relationship on the masses between the various particles, including this background field. So what I wanted you to derive is the relationship between the eta prime, the A naught, the sigma, and the pi. And in fact, there's a trick. The trick is the following. The symmetry here is SU 3 left plus SU 3 right plus axial V1. And what you can show is that the thing that will break. So what you really have to do is you have to take phi is equal to some sigma naught times the unit matrix plus that. This is assuming H is linear. So this is H is 1, 1, 1. And then you have to expand in small fluctuations. You compute how each term contributes. And you go from there. But in fact, what I realized is that you only have to look at the expansion of this term, because this is the term that breaks the axial V1 symmetry. This is the term that will split the eta prime from the pi. So if we just want to look at this mass splitting, we can just look at the expansion of that term. And that's what the exercise was then. In fact, and now you have to be careful with the generators. That's why I gave you the generators. You have to make sure that the generators are normalized. And so the simplest thing to do is to take generators that are only diagonal, because then you don't have off-diagonal generators. And so for pions, you can take this, since P3 squared is equal to 1/2. So if I square this, I get 1/4 times 1 plus 1, which is 2. And then for the diagonal generator, you have to take 1 over the square root of 6 times 1, 1, 1. Because again, if you square this, trace of T naught squared is equal to 1/6 times 3, which is 1/2. So you have to take that. Because what you want to do is you want to compute to quadratic order. What you want to do is compute phi is equal to sigma naught plus I eta naught times T naught, where this is this generator here. And then we want to look at the A naught field and the pion. This is, of course, just the neutral pion, but that's good enough because we know the other masses will all be equal. And in fact, if you notice that it's just going to come from this symmetry breaking term, it's easy to work that out. And let me do that for you now. So all of the other factors will contribute to the overall masses, but they won't contribute to the masses that contribute to the 't Hooft relation. So what we need to evaluate is the following. If I put in the generators properly, I get 1 over the square root of 6 times sigma plus I eta plus 1/2 A naught plus I pi. Okay, that's 1. 1 over the square root of 6 sigma plus I eta plus 1/2 minus 1/2 A plus I pi. And then lastly, 1 over square root of 6 sigma plus I eta. And I want to calculate the determinant of this matrix, but I just have a product of 3 things. And you can see it simplifies pretty easily because this is minus that. So what I'm going to get is 1 over the square root of 6 sigma plus I eta plus 1/2 A plus I pi. But then I'm going to get minus, so what I'm going to get, let me take out the 6 here. I'll take that out everywhere. And I'm going to get this times this is going to be this times that complex conjugate. So I'm going to get sigma plus I eta squared minus, because this is plus minus, square root of 6 over 2 A plus I pi squared times sigma plus I eta. And I'm being sloppy with the overall notation, overall normalization, because it won't matter. And what do I get then? Well, this is just equal to sigma plus I eta cubed minus, and I think I did it right. This is the square, 3/2 sigma plus I eta times A plus I pi squared. Okay? This is determinant fine, but now what I want to do is add complex conjugate. So what this is going to do is give me something that's like, well, I want to pick out the real parts from this. So I'm going to get sigma cubed here. I don't have to worry about the sigma, the term with 2 sigmas and 1 eta over 3 etas, because that's purely imaginary. So I get minus 3 sigma eta squared. And then I think you can show minus 3/2 sigma A squared minus pi squared. And there's one last term that's minus 3/2 eta A dot pi that also contributes, but this won't matter because, well, all we want to do is look at the masses. So this is what the term is in general, and now we simply want to expand about some expectation value of sigma, and we don't even have to know what that expectation value is. If we do that, and I've done the algebra correctly, which is always always questionable. What I will get is something like, if I have minus determinant phi plus complex conjugate, what I will get is something like minus 3 sigma naught. And so now I'm expanding, sigma goes to sigma naught plus sigma. So that's where the 3 comes from. Times sigma squared minus eta squared plus 3 halves sigma naught pi squared minus a naught squared. Okay. I think that follows from there. Okay. And again, what we want to show, what I asked you to show, is to look at to show that you have the relationship that the mass squared of the eta minus the mass squared of the pion is equal to the mass squared of the A naught minus the mass squared of the sigma. That is, this is the eta prime. As the eta prime gets driven up by the anomaly, the sigma gets driven down, and you can just read off the contributions to here, because the contributions are going to be proportional to 3 times sigma naught. For the eta prime, it's minus times minus, which is plus 1. For the pion, it's minus times 1/2. I've taken out an overall factor of 3. So that's minus times minus 1/2. For the A naught, that's minus times minus with a 1/2. And then finally for the sigma, that's minus times minus. And so in all, we have 3 halves equal to 3 halves. And so we can see a perfect relation without going through all of the algebra of working things out. And it also shows you that this relationship is probably true in the general. Okay, are there any other questions? That's pretty much it. It's the end of the day. You guys deserve a break. I think all of you have actually been pretty good at this. Especially those of you who were up late last night. That I'm particularly impressed with. But I really suggest you look at Cvitanovic's book on bird tracks, because he derives things in great generality. And it's really a useful trick. Otherwise, you carry around indices with like products of TABs and FABCs, and it's very confusing.
All right, more questions? Well, if not, then let's thank Professor Pisarski for his nice lecture.